Assalamualaikum and hi everyone. So for this introduction, I'll represent about the theory behind the Green's Theorem. So the Green's Theorem was founded by George Green. In 1828, the George Green published his work, which is now known as the Green's Theorem. During those days, the theorem went practically unrecognized. It is because the theorem was too advanced during those days. In 1846, Augustine Louis Cauchy, who was another well-known mathematician from the 19th century, has proved the Green's theorem. As we can see in the formula attached in the slide, the C in the formula represents a closed, bounded, and positively oriented simple curve. As for the P and Q, it is represent continuous function with continuous first partial derivative on some open set containing C. So for this section, we will start with the first question out of two questions that we have been prepared for this slide. So in this question, the question asks to use Green's theorem to evaluate the equation where C is negatively oriented as shown in the slide.
Manual calculation for question 1. We need 3 steps to answer this question. The first step, we need to find the derivative of p with respect to y and derivative of q with respect to x. From the integral given on the question, we can express the equations of p and q separately. For p is equals to x cubed minus xy with dp over dy equals to negative x. And for q equals to 6y minus 9x with dq over dx equals to negative 9. For the second step, we need to find the equations of y1 and y2 where the limit of x is from 0 to 4. For y1, we will apply the general equations of line for coordinate for negative 8 to 0, 0. First, we need to find the value of m, which is the gradient, by using the formula of y2 minus y1 over x2 minus x1. Then we substitute all the values by using the coordinate that I have mentioned just now. Then we get the answer of m is equals to negative 2. Then we find the value of c by using the general equations of line again and substitute the value of x, y equals to 0, 0 and value of m is equals to negative 2. Then we get the answer of c is equals to 0. And finally, equations of y1 equals to negative 2x. For y2, we will apply the same calculation that I have did just now, but for different coordinate, which is from 0, 0 to 4, 2. Now we get the answer of m is equals to 1 over 2, c equals to 0, and finally, the equations of y2 equals to 1 over 2x. Step 3, we need to find the value of line integral by using the Green's theorem formula. By using the Green's theorem, we define integrations of f dot dr equals to double integral of dq over dx minus dp over dy. But we need to notice that this part on the question does not have a positive orientation. It means that we can actually use directly Green's theorem to evaluate the given integral. However, if c has a negative orientation, then negative c will have the positive orientation. And we know how to relate the values of the line integral over these two curves by adding the negative sign on the front of the integral. Therefore, it can be expressed as negative of double integral of negative 9 plus x with respect to y and with respect to x, where the limit of y is from negative 2x to 1 over 2x, and limit of x is from 0 to 4. For the final answer, we got 380 over 3.
Firstly, we begin by restarting the Maple session with the restart command. This clears all the variables and settings, ensuring a clean workspace. Next, we load the linear algebra package to access matrix and vector operations. Then, we define function p as p equals to x power of 3 minus xy. Similarly, for the function q, which we define as q equals to 6y minus 9x. These definitions are confirmed in the outputs as expected. After that, we differentiate p with respect to y and we will get negative x. And we differentiate q with respect to x, then we will get negative 9 as shown in the output. To define the region of interest, we specify constraint negative 2x to x over 2 defines the bounds for y, and 0 to 4 which defines the range for x. These constraints set up the area for integration. Then we evaluate the double integral command as shown in the slide. Since it was negatively oriented, we put negative sign in the formula and the output we will get is 380/3. Finally, we visualize the constraints using the plot command. We use the command of f equals to map and apply for x to the power of 3 minus xy and 6y minus 9x, where we define R1 as t and negative 2t, for R2 is t and 1/2t, and for the R3 is 4 and t. Then, we plot the graph command as shown in the slide. The graph plots 3 curves as in the outputs. And for the curves with green color is for y equals to negative 2x, the blue color is for y equals to x/2, and the gray one is for boundary segment. The graph clearly shows the region of...
Continue with the question 2, where the question states that C be the piecewise smooth curve, or composed for the C1, C2, and C3 as shown in the slide, with a vector field given.
Manual calculation for question 2. We also need 3 steps to answer this question. The first step, we need to find the derivative of p with respect to y and derivative of q with respect to x. We can express the equations of p and q separately from the integral given on the question. P is equals to x squared with dp/dy equals to 0. And for q equals to y minus x with dq/dx equals to -1. For step 2, we find the equations of y at C3, where the interval of x is from 0 to 1. We will apply the general equations of line y equals to mx plus c for the coordinate 1, 2, 2, 0, 0. We find the value of m, which is the gradient, by using the formula y2 minus y1 over x2 minus x1. And we substitute all the value by using the coordinate that I have mentioned just now. Then we got the answer of m equals to 2. Then we find the value of c by using the same general equations of line by substituting the value of xy equals to 0, 0, and the value of m equals to 2. Then we got the answer of c equals to 0. And finally, the equations of y equals to 2x. For step 3, we find the answer by using Green's theorem formula, which equals to the integral of dq/dx minus dp/dy. Then we substitute all our findings on that formula, which equals to double integral of -1 with respect to y and respect to x. And also, with the limit of y is from x squared to 2x, and limit for x is from 0 to 1. And finally, the final answer is equals to -2/3.
Next, I will explain the maple commands and outputs used in solving for question 2. We begin by restarting the maple session with the restart command. This clears all variables and settings, ensuring a clean workspace. Next, we load the linear algebra package to access matrix and vector operations. The function p is defined as p equals to x to the power of 2. Similarly, for function q is defined as q equals to y minus x. These definitions are confirmed in the outputs as expected. Then, we differentiate p with respect to y, and the derivative is equal to 0. Next, we differentiate q with respect to x, and the derivative is -1 as shown in the output. To define the region of interest, we specify constraints. X to the power of 2 until 2x defines the bounds for y, and 0 to 1 defines the range for x. These constraints set up the area for integration. Then, we evaluate the double integral as shown in the slide, and the output for the command is -2/3. Finally, we visualize the constraint using the plot command. We use the command of f equals to map and apply x power of 2 and y minus x, where we define R1 is equal to t and t power of 2, for R2 equal to t and 2t, and for R3 is 1 and t. Then, we plot the graph command as shown in the slide. The graph plots 3 curves as shown in the output. From the graph, we can see that for the purple color is y is equal to x power of 2, and the red color is for y equals to 2x. The graph clearly shows the region of the interest.